So hello everyone, welcome back to our Wednesday seminars. So today as a guest speaker we have Eric Giunchi from University of Bologna. He is a postdoctoral fellow working with Professor Nipoti and Federico, focusing on n-body simulations of globular clusters, progenitors, both in specific objects like the sparkler galaxy or by means of cosmological simulations. And today he will be discussing us with about his ongoing research on star formation in near stellar clumps of round pressure strip galaxies as seen by HST. So without any further ado, let's welcome Eric.
Yeah, thank you. Thank you very much for the introduction and the invitation. So yeah, as the title suggests, I'm going to talk about stellar clumps, but in these specific kinds of objects, so galaxies that live in galaxy clusters and that are undergoing round pressure stripping. Most of the results are published in these 5 publications that you see here. That, of course, at the end, there is also some ongoing work. So to give an introduction of all the different blocks of the work, we can start, of course, with the stellar clumps that are very important in modern astrophysics because we know that stars do not form, let's say, uniformly and widely in the disk of galaxies, for example, but they form very clustered in these stellar clumps that are, we can say, a sort of bridging scales between the large-scale structures of galaxies and really the birth sites in which we form the single stars, because they are the smallest regions that we can treat as stellar populations, but at the same time, they can be simple stellar population. They are forming single bursts of stars. So they can be very small, a few parsecs in size, up to a kiloparsec, and also small in mass, 1,000 solar masses, up to 1,000,000. And you can see them in these images, both in a disk galaxy of the Funks collaboration, but also in these disturbed starbus galaxies from the Lars sample. So we think that they form thanks to the turbulent cascade. Essentially, the interstellar medium of galaxies cools down, and driven by turbulence, it creates these smaller and smaller structures and clouds in which we finally form the clumps. These should leave a footprint in the mass function of the young stellar clumps that should be described by a power law with slope -2, in some cases also with a hint of a high mass cutoff. And indeed, as you can see in this plot that is from the review by Krumholz et al. In 2019, many works that study the mass function of clumps tend to find the slope that are consistent with this predicted value of -2, confirming the possible nature of the gas collapse that drives the formation of these clumps. These are other examples from main sequence galaxies in the LEGUS collaboration. You should see all the blue dots that here are clumps, so groups of stars, but also some other extreme cases like starbus galaxies from the dynamo sample, or high redshift clumps in these very high redshift galaxies. So, of course, these can look very different, could be both for observational reasons, but also for intrinsic reasons. And indeed, we think that there are some properties that can vary in the clumps according to other parameters. For example, the nature of the galaxy in which they form. For example, in this work by Fisher et al. 2017, they compare the star formation rate surface density of clumps in main sequence galaxies that you see in green with clumps of the dynamo sample, so starburst galaxies, galaxies that are forming stars with a very high star formation rate compared to other galaxies of similar mass. And indeed, as you can see, also the clumps have different properties. The sigma star formation rate is larger. So the clumps are not uniform, let's say in the universe, they're not always the same. Also the redshift can play a role. For example, in this work by Livermore et al. 2012, they compared the mass function of a high redshift sample of galaxies in blue with samples of clumps from the local universe. And as you can see, the mass function in blue at the high redshift can reach larger values in mass on the top axis, or H alpha luminosity, compared to the local universe. So this is because in the high redshift, the environment is different, the galaxies are different, and also the clumps are affected. Or we can have also the effects of the environment. There are two results here. On the top right, the luminosity size relation of this collection of clumps from many different works that Cousins et al. Put together. And as you can see, there are two different trends in blue, let's say, and in golden. And these are clumps that are distinguished for having a different star formation rate surface density, as I said before. So, as I said before, these should be clumps belonging to starbus galaxies, and they also have a different luminosity for a given size compared to the others. So these are really differences that could be important because these clumps are very, very bursty in forming stars. Or in the middle, you can see these luminosity functions by Ness et al. 2019, in which they compare the luminosity function in green of clumps that are in the spiral arms of galaxies with the same quantity, the luminosity function, of clumps that are in the interarm regions. And as you can see, there is clearly a difference. The green luminosity function is flatter, and so there is a difference in the luminosity distribution, whether we are looking in regions in which there is ongoing star formation or in regions that are more passive, like the interarm region. And it is important to really study how the clumps evolve because clumps can affect the morphology of galaxies according to how long they survive. If they merge to the center, they migrate to the center, they can contribute to the formation of the bulge, but all of these depend on their properties. And that's why it's very important to understand really what drives their formation. The second ingredient of the work are the clusters, so the galaxies in cluster, and so the clusters of galaxies more in general. So we know that they are the most massive virialized systems in the universe, 10 to the 13, 15 solar masses, and they are very peculiar environments in which we can study the effects on star formation, because all of the galaxies that live in clusters can undergo many different processes that can really help in quenching their star formation. So, for example, starvation, that is essentially the phenomenon according to which the galaxy cannot accrete cold gas anymore from abroad because the intracluster medium in clusters is very hot and very dense. There is also the strangulation. Because of conduction, the gas that is in the galactic halo cannot cool down anymore, and so also this reservoir of cold gas is completely stopped. Or we have also fast encounters with other galaxies in the cluster that have also the effect of heating up the gas and stellar components, so again preventing the gas cooling and therefore the formation of new stars. And finally, the focus of my work, which is on the ramp pressure. So in particular, when a galaxy falls and is firstly accreted by a cluster, it experiences for the first time the impact with the intracluster medium that is typically denser and hotter than what we see in the field. And so we have a ramp pressure that is given by the density of the medium and by the velocity of the galaxy. And if we compare it with the gravity of the galaxy, we are essentially understanding if the push of the gas is larger than the capability of the galaxy to retain the gas. And if the ramp pressure is larger, the interstellar medium of the galaxy will be stripped away. And we do have evidence, nowadays, a lot of evidence of this kind of process. For example, here you can see this optical image in blue with the ALMA emissions, so molecular gas in red. And you can see these tails of molecular gas, also a bit clumpy. Indeed, that's why these galaxies are also called jellyfish galaxies because of these tentacles. And the interesting part is that this is a purely hydrodynamical process. And indeed, as you can see, the stellar component, this is the velocity map of the stellar component of the galaxy, is very smooth and very similar to what we would see in a main sequence galaxy, because the stars are completely untouched by this kind of process. Also, if we look at the ionized component of the gas, so the H alpha, you can see that there is not only emission in the disk, but also in the tail, and the emission is not only diffuse, but can be also clumpy. So this means that there is not only diffuse ionization, but also ionization coming from ongoing star formation. These are really stars that have formed in gas that was stripped far away from the galaxy. So they're really stars that are forming in a peculiar environment compared to the field galaxies, because they are far away from the galactic disk and they are surrounded by the intracluster medium. So the environment is very different, and therefore that's why we're interested in understanding if the clumps that are forming here are different from those that we see in other kinds of galaxies. So the starting point of the work was the GASP survey that observed with MUSE about 100 jellyfish galaxies. Here you see 6 of them that are the same that will be observed also with HST, as you will see. So MUSE is very powerful because it can operate with the integral field spectroscopy, so it can give us photometry and the spectrum of each pixel, spaxel, at the same time. So we can really have for each spaxel of the image the spectrum. And this is very important to trace the ionized gas and also the stellar component. However, the problem, let's say, when we want to study clumps, is that the resolution is only 1 kiloparsec at the redshift of these objects, about 0.05. And so this is not enough, and that's why we also observe these galaxies with HST. However, MUSE is still very useful because, for example, using, as I said, the spectra, we can distinguish the regions in which the H-alpha emission is powered by star formation in red, and separate all the other regions, exclude all the regions in which the H-alpha is powered by other mechanisms, such as the AGN and shocks, because we really want to focus only on the regions in which we have ongoing star formation. So the 6 galaxies that you have seen before have been observed also with HST, in particular in these 5 photometric filters that cover the optical bands, but also the near UV bands that are very important because, as you can see from these spectra, they can really help us in distinguishing different ages for the clumps from 0.01 gigayear to 1 gigayear. And also, thanks to this narrow band, putting everything together, we are able to trace the star formation in the clumps in 2 ways. We can use the H-alpha and we can use the UV. And they're important because they trace different star formation timescales. Very young objects for H-alpha, 10 megayears, because we need to have OB stars that are able to ionize the surrounding gas, or 200 megayears in the case of UV, because we can also trace, let's say, less massive stars that are still bright in UV, but not enough to ionize the gas. So these are the 6. They are the same one that you've seen before with MUSE, but now these are the RGB images of HST. So you can appreciate the improvement in spatial resolution, and also all the blue dots that are all the UV clumps that we can now see with a much better resolution. And you can see them placed not only in the disks, but also in the tails of these galaxies. So the idea is really to detect them now and compare them with each other and with, of course, literature. So in order to do that, we performed the detection using Astrodendro. As I said, we did it both for the H-alpha and UV. For example, this is JO201 that was on the top left, and this is the H-alpha map of JO201. So you can see that Astrodendro, for example, on the bottom right, is able to detect very bright and wide regions, but also sub-regions inside, so like secondary peaks in yellow. And from the different colors, you can see that we defined 3 different spatial categories. The disk clumps that are in the innermost regions of the disk, that are clumps that look essentially undisturbed. And the clumps in blue are in the extraplanar region, so they are in the outskirts of the disk, and they already look asymmetric, elongated, so we thought that they could form from gas that was already been stripped, but maybe still overlapped to the optical disk because of projection effects. While in green, you see all the clumps that are outside of the optical disk, and so for sure these are the so-called tail clumps. So these are clumps that formed at 100% from gas that was already stripped. So we can now compare these different spatial categories. Another interesting thing that we can do with jellyfish galaxies is also to detect optical regions in the tails, because we are not contaminated by the disk anymore. And so you can see in violet the optical regions, and we just require them to be matched with at least one UV or H-alpha clump in purple or golden to just confirm that it is UV emission correlated to the phenomenon that we are seeing and not anything in the background or foreground. But these are important because essentially it can give us the whole stellar mass that has been formed in the tails of these jellyfish galaxies. So to give some numbers, in H alpha, we detected about 2400 clumps, almost 4000 in UV. Most of them are in the disk, but we have hundreds of them also in the extraplanar and tail regions for both the samples. And for all of these clumps, we have the measurements in the 5 filters that I mentioned before. Furthermore, 15% of them are resolved, so they are much larger than the the angular resolution of HST, that is about 70 parsec at redshift 0.05. It's quite impressive because it means that 85% of these objects are smaller than this value. So it means that they tend to be very, very small. In addition, we have also 400 optical complexes that, as I said, are only details. So the first thing that we can do is select only the resolved H-alpha clumps. Indeed, you can see that the numbers are much smaller now, about an order of magnitude smaller. And we can put them in the luminosity size relation. The first thing that you can see is that the 3 categories, red, blue, and green, overlap with each other. So we cannot distinguish the special categories just by their position in this diagram. This is interesting because, again, tail clamps are in a very different environment from the disk, but still there are no variations with respect to those that we see in the disk. However, if we compare them with literature results, you can see in black clumps that are in main sequence galaxies, and the blue contour are clumps that are in starbus galaxies. And as you can see, our clumps lie a bit in between, but much closer to the clumps that we see in starbus galaxies. This is interesting because it means that also these clumps are enhanced in star formation rate surface density. And it kind of makes sense because ramp ratio stripping could be able to compress the gas and therefore cause this enhancement in star formation rate. But at the same time, it's not a process as violent as a merger, that is the process that tend to trigger the starburst event. So it kind of makes sense that they lie in between, but still with a certain enhancement. Then what we can study is also the morphology of the clumps in the tails. So in particular, also previous works found out that we can expect a specific morphology, a specific configuration in the tails, because again, as I said, ramp ratio stripping acts only on the gas component, while the stars, once they formed, they are completely untouched by the ramp pressure. So if we think about a gas cloud that is in position number 1, it will form these stars, it will deposit the stars here, and then it will be pushed to position 2 while the stars will remain there. And so on also in position number 3. Where it will form the youngest stars of the sample. So we should expect, in principle, a trend with age in which we see old stars closer to the disks compared to young stars. And this is reflected also in the photometry. So red stars will be close to the disk, while UV stars a bit in between, and H-alpha bright regions very far away from the disk. And this is also a bit observed in this work in which you can see the very compact H-alpha emission with these UV tails pointing towards this disk. And so we expect young stars to be displaced more farther away. And we do see them, at least qualitatively, also in our RGB images. You can see always the H-alpha head, let's say, pointing far away from the disk with these UV tails pointing towards the disk. They can be a bit clumpy, they can be more diffuse, maybe the H-alpha is not always as bright, but it kind of is there, but now we want to quantify it. So we can take this complex, for example, as a starting case, and we can try to understand which are the quantities that could help us in finding out these properties. So, for example, we can take the filling factor of all the clumps in a certain filter. For example, this is the UV filling factor, the area of the complexes that is covered by the UV clumps, and also for the H-alpha. Or we can study the geometric displacement. We can take the brightest UV or H-alpha clump and compute the distance from the center of the complex. And in principle, we expect the H-alpha displacement to be larger than the UV displacement because the H-alpha is tracing only the very young components, while in UV we have a broader interval of ages. So if there is a spread spatially correlated to the spread in age, we should see the UV clumps a bit closer to the center of the complex compared to young stars only. So we can study the cumulative distributions of these two quantities. So in gold, you have the distribution of the H alpha filling factor, and in purple, the distribution of the UV filling factor. And you can see that on average, the H alpha filling factor is always smaller, on average 10% compared to the 25% of the UV clumps. And also, most of the H alpha clumps can cover less than 40%, while in UV we can reach larger values. So we do see that UV clumps tend to cover a larger area of the complexes compared to the H alpha. On the other hand, the situation is opposite, but as expected, when we look at the displacement, now the yellow curve is more at larger values than the UV one. And so this means that on average, typically the H alpha clumps are more displaced, more on one side, on one edge of the complex with respect to the UV clumps. So these are hints of the fireball configuration that we've seen, but we have more evidence of it. For example, we can study the correlation of the displacement with the area of the complex or the elongation of the complex, the axial ratio, so more elongated to the left. And we can see that the H alpha displacement is always larger, but they also increase as we look at large and elongated complexes. So essentially, when we look at an elongated and large complex, the clumps do not tend to be at the center of it, but they are always on one side, with the H alpha more displaced than the UV. So this is essentially what we saw also in the first case that I've shown to you, but this could have been like a special case, a very good case, but statistically, since here there are all the clumps of the sample, this happens for all of the complexes. So this is interesting because it's the first systematic evidence of it. Before, we had to check each complex one by one, but of course, if we increase the sample, we cannot check each of them one by one to understand which is the direction of it. These are general quantities that still work and show the evidence of this morphology. Then we can move to the estimate of the masses and ages of the clumps. As I said, we have the 5 filters. You can see them here, the 5 photometric filters of HST. And using backpipes in this work by Verle et al. 2024, we obtained the posterior distributions for the mass-weighted ages, the stellar mass, the star formation rate, and the extinction for H alpha, UV, and optical complexes. This is the same complex that we've seen before with 1 UV and H alpha clumps, and these are the results. So we can have finally a catalog of masses and ages for most of the clumps. It depends on the quality of the data. So just to show some distributions, these are the same colors that you've seen before for H alpha, UV, and optical complexes. And as expected, typically H alpha clumps are younger and less massive than the UV or optical counterparts. So let's say everything is working as expected. But what I wanted to focus the most is on the clump mass function. As I said, it's a very important observational quantity that we can obtain to understand how clump form and what are the variations compared to what we see in field galaxies. Because as I said, we expect a power law with slope -2, maybe with a cutoff, depends on the quality of the data and on what galaxy we are observing. But variations in the slope can imply a lack or an excess of massive clumps, and therefore it becomes interesting to understand what can cause these variations. As I said, the quality of the data is very important, and that's why we could focus only on the tail and extraplanar clumps, both in H alpha and UV, because in the disk, the contamination from the older stellar components was too important to have good estimates of the stellar mass. So before looking at the stellar mass, just to show you how important it is, the analysis, if we just take the luminosity function and we bin the clumps in luminosity, so this is essentially the number of clumps with a certain luminosity, and if we fit a line in this plane, we get slopes that are 1.8, 1.9. So also for the UV, you can see here the squares. These are all slopes that are smaller than 2. So in principle, one would expect that we have an excess of bright and massive clumps because the luminosity function is flatter than expected. However, these are quantities that are highly affected by blending effects. The clump could overlap on the plane of the sky, or for example, we cannot observe very faint clumps. And these are all quantities that we need to quantify, otherwise the estimate of the slope will be biased. So we focus on two main factors that can bias our results: the completeness, as I said, the capability of detecting low mass clumps and to distinguish clumps when they are blended together, and also the discrepancy between the real intrinsic mass of the clumps and what we get from the observations. That depends on the modeling, on the detection, etc. So we created a mock library of mock clumps that given a mass, an age, and an axial ratio can give us the shape, so the physical shape of the clump in the image, the size of it, and also the spectral energy distribution. And this is all based on the real data that we have. We threw 1,000 mock clumps per galaxy using this grid, of course, multiple images, and we can perform again the same procedure to detect the clumps that were used for real clumps. And so what we will have is that some clumps will not be detected, and so we will check what are the masses that we are losing, while for the clumps that are detected again, we can compare the intrinsic values that we assigned a priori with the result of the observations and of the analysis. And these are the two results. So the completeness to the left, so we can see that we are more and more capable of detecting clumps as we get to high masses. So, of course, we reach 100% and we decide to stop the completeness, so to exclude, essentially remove all the clumps that are less massive than this threshold value, because this is below the 50%. So essentially the data can become very, very noisy and uncertain. It's also interesting to look at the discrepancy. This is the comparison between the intrinsic mass on the y-axis and the observed mass on the x-axis of all the mock clumps that we were able to redetect. And you can see that there is a good agreement at high mass. So our data analysis is able to retrieve the same mass as the intrinsic one. But in the low mass regime, we tend to underestimate the real mass of the clump. So we can essentially, given an observed mass, given the mass of a real clump, we know the observed mass, but we do not know the intrinsic one, but we can build a sort of Gaussian distribution, taking the clumps that are located here in this narrow region, that essentially give us the distribution of possible intrinsic masses at a given observed one. So these two quantities can now be used to correct the mass function. So the mass function has been fitted in a Bayesian way using MCMC. So the only, let's say, the only independent quantity is the observed mass of the clumps, and the free parameters are those of the mass function that is completely arbitrary. We can put whatever functional form we want. And this is the likelihood. So there are the three main components, so we can recognize the completeness and the discrepancy, and this is the mass function. So we tested a single power law. The only free parameter is the slope alpha, or a Schechter function that, in addition to the power law regime, has an exponential cutoff. And so you can see that for each clump of our sample, we have a certain observed mass, and we have this single likelihood, which is in the natural logarithm. So we integrate over the whole interval of input masses that are weighted by the Gaussian. So for each input mass, we know how likely it is that that input mass result in the observed mass that we see, thanks to the Gaussian distribution that I've shown before. So this is the likelihood of a single clump, the probability of observing a clump with that observed mass, given the parameters also of the mass function. We sum together all the likelihoods of all the clumps of our sample, and this is the likelihood of the mass function. We vary the parameter of the mass function until we maximize the probability of observing the sample of clumps that we have. And these are the results. These are just histograms because it's the distribution of the slope of the power law mass function. So what we can see, first of all, is that now the slopes are larger than 2. So the correction have been very, very important, because from slopes that were smaller than 2, now the corrected ones are larger than 2. And so this means that we have a lack of massive clumps, both in the tail and in H alpha, but also in UV and in the extraplanar regions. It's also interesting to see that the UV mass function is steeper than H alpha 1, and this could be caused by the aging of the clumps. The clumps in UV can be also older, so they have time to evolve, to get disrupted, to merge together, etc. And this can change, of course, the shape of the mass function. But also we can see that in the extraplanar region, the slope tend to be slightly larger. They're still consistent with each other, but there is this tendency. And this could still due to observational effects that are maybe more difficult to quantify in the extraplanar region, in which we are already a bit contaminated by the disk. But it could also be due to the fact that maybe in the tails, there is something happening that is not happening in the extraplanar region. So, however, the take-home message is that the mass function is steeper than 2, and so we have a lack of massive clumps. So these can raise the question of what caused this lack of massive clumps. Either they can be quickly destroyed as soon as they form, so we do not see them even in H alpha, or on the other hand, there could be other effects that can completely prevent the formation of massive clumps. And for example, there are these works by Lee et al. And Iniesti et al. 2023 and 24, in which they found out, looking at the ionized gas in jellyfish galaxies, that there is evidence of mixing of the interstellar medium with the intracluster medium. And the fact is that the intracluster medium is very turbulent, so it can destroy clouds of interstellar medium, even of 1 kiloparsec in size. So essentially, the intercluster medium is able to destroy the largest clouds of the interstellar medium, and those are the clouds in which we expect to form the real massive clumps. So this is a very interesting scenario that could justify the absence of massive clumps. Essentially, their birth sites are completely destroyed by the environment. And again, this is what we were looking for, environmental effects. And now I would like to focus on some ongoing work, because when I moved to Bologna, I became more of a theorist, so focusing on simulations. And I would like to start with this previous work by Guglielzik et al. In 2020. In this work, they used the GASP data to compute the average star formation rate that is occurring in the tails of jellyfish galaxies per cluster. So essentially, they put together all the jellyfish galaxies in a cluster. They did that for many clusters that were complete in sample. And so they found out that on average, the star formation rate, so the injection of stars in the intracluster light from the jellyfish galaxies, is 0.22 solar masses per year. So if we put together all the jellyfish galaxies in a cluster. This is instantaneous, so if we integrate for the accretion history of a cluster, we can obtain all the stars that have accumulated in the intracluster light because of the jellyfish phenomenon. And they found out that since Redshift 2, the jellyfish have brought about 4 billion solar masses of stars in the intracluster light, which is really a small fraction of the total intracluster light. So this is negligible. But the question is, we know that some of these stars are grouped together in clumps. And we know also how many of them, because there is a previous work by Tomicic et al. 2021 that showed that in the clumps we have 10% of the ongoing star formation that we see in the tails. So the tails are very diffuse, but there are some clumps. And we want to understand what happens to them, if they can survive, and in particular, if they become in a sort of wandering objects that start orbiting in the cluster far away from the parent galaxy, but also from the central region of the cluster, from the bright central galaxy at the center of the cluster. So there are, of course, simulations that study the formation of clumps in jellyfish galaxies, but these simulations are very expensive because, of course, to study their formation, we need to perform hydrodynamical simulations, and as you've seen, the phenomenon is very complex. The gas is being stripped, there is mixing with the intracluster medium, there is run pressure. So these simulations can really study only the first instance of formation of clumps, and also they cannot study all the parameters that can affect the formation of clumps, like, for example, the mass of the parent galaxy. And on the other hand, if we want to recover these statistics, so study multiple galaxies of different mass, etc., we need to simplify the problem in another way. So, for example, we can think of the clumps when they have already formed. So, for example, if we think of UV clumps as you have seen them in the HST images, they are old enough to be gas-free and to be already little affected by stellar evolution. All the mass expelled by OB stars has been already expelled. So they can be taken, let's say, as stellar-only components, and this is very useful. Also, one should simulate them as resolved to study their tidal stripping evolution. But again, this is an ongoing work, so as a starting point, they are point mass particles. And then we put them in a cluster. So there is the cluster gravitational potential. To start, we simulated a cluster of 10 to the 14 solar masses, so a low mass cluster. But it's constant in time. And again, this is another strong assumption because we know that clusters can evolve a lot in mass from redshift 2. So one should also somehow take into account the redshift evolution, and we will do it, but this is again a starting point. Then there is the galaxy gravitational potential, and here is where we can exploit the assumption that we did, because we can study 6 different masses for the galaxies, and also we can study the fact, we can include the fact that as the galaxy fall onto the center of the cluster, it gets more and more truncated, so it shrinks in a sense, and this will help the clumps in escaping them. Then we have many different orbits for galaxies. Galaxies are accreted by clusters, and we have these simulations, for example, by Smith et al. 2022, in which we have the distribution of radial and perpendicular velocities of the galaxies as they are accreted by the clusters, compared to the cluster velocity dispersion. So this can give us the variety of different orbits that a galaxy can have. Also, the clumps form constantly during the orbit, and so we not only simulated all these different orbits, but we also started from 4 initial positions along the orbit, so like very far away from the pericenter up to the pericenter itself, it creates different conditions. Finally, we need to assume an initial position and velocity for the clumps, and we decided to place them at the truncation radius that we have at the pericenter, so the minimum truncation radius. The idea is that if a clump wants to become a wanderer, so to become an independent object, it must at least cross this minimum value, because if it always remains and lives inside the truncation radius at the pericenter, so the minimum truncation radius that we can have, for sure it will remain bound to the parent galaxy. The initial velocity can go in principle from 0 to the same velocity of the galaxy, and this represents 2 extreme cases in which we have a super strong ground pressure stripping that completely decelerated the cloud from which the clump formed, or when we had the same velocity of the galaxy, essentially the cloud underwent a very mild ground pressure stripping, so it was pushed away from the disk, but still retaining a similar velocity to the one of the galaxy. So now we have all the ingredients to perform our arepo simulations and see what happens to these point mass particles, including all these quantities. So just to show a cartoon, imagine to have this orbit. This is one of the many orbits that we can have. And these are the 4 initial positions. So as I said, very far away from the pericenter, 0.7 R200, so like the virial radius of the cluster. Then we have the pericenter and also an initial point, initial position that is after the pericenter, because we know that the jellyfish phenomenon can last also a bit after the pericenter passage. And in all of these points, we will place the clamp at the minimum truncation radius even if the galaxy is less truncated than that. But you can see that as we start closer to the pericenter, also the initial truncation radius of the galaxy will be smaller and smaller. And as the galaxy will approach the pericenter, it will also get more and more truncated. The green is the velocity, the green arrow is the velocity of the galaxy, and the red arrows are all the possible values of the initial velocity of the clumps, from 0 to equal to the velocity of the galaxy. So as you can imagine, these are a lot of simulations because we have tens of orbits, and we have 4 initial positions for each orbit, 5 initial velocities for each clump, and 6 different values in mass. So in total, there are, if I remember correctly, there are like 5,000 little simulations that are very fast, but there are many. And for each of them, we can trace the position of the clump in time. So we can take, for example, this diagram in which you have in orange the position of the galaxy, the distance of the galaxy from the center of the cluster, that is the orbit of the galaxy, essentially. In blue, the orbit of the clump under the effect of both the gravitational potentials of the galaxy and the cluster, and in green, the distance from the clump from the center of the galaxy. So for example, as you can see here, the clump is slower in this case than the galaxy, so it reaches the pericenter after the galaxy, and you can see it also in the fact that the distance between the galaxy and the clump increases with time. So at the end of the simulation, we can, in a sense, decide if the clump has become a wanderer or not. And there are, let's say at the moment, we have decided for 3 possible conditions for which the clump is not a wanderer. The first case is if at a certain point, the distance of the clump from the center of the galaxy, of the cluster, is smaller than 10 kiloparsec, because we assume that it got too close to the bright center galaxy, and so it got accreted by the BCG itself. Or if it crosses the galaxy at least once, so if it gets too close to the center of the galaxy as well, destroyed the clumps. So also these clumps did not survive at all. The final scenario is the case in which the clump remain bound to the galaxy. So the distance between the galaxy and the clump is always very small, less than the truncation radius, and so this clump couldn't escape its parent galaxy at all. So given the results of these simulations, we have for that simulation if the clump is a wanderer or not. If we want to put together all the, if we want to understand which is the total mass that is being deposited in wanderers, we need to perform this long series of integrals, but actually the components are quite simple. This is just the mass accretion history of the cluster, so the same one as in Guglielzik et al. 2020. The total star formation in the tails, the famous 0.22 solar masses per year that I've told you about before. The 10% that is the fraction of star formation in the tails that is occurring in the clumps, so the Tomicic et al. Result. And these are the distribution of radial and perpendicular velocity of the galaxy from Smith 2022. Essentially, these give a weight to the orbits. It tells us if the orbit that we are simulating is more frequent than others, because we perform one simulation for each orbit, but some orbits are more common than others. Then we have the Schechter function for the mass, the stellar mass of the galaxy, the distribution of the stellar mass, because again, we simulate each let's say each galaxy. For each galaxy, we perform only one simulation, but of course, low mass galaxies are more frequent than high mass galaxies, so those are simulations that, in a sense, happen more frequently than others. And then we have these 2 weights that come from our assumptions in the simulations. So the first one, this orbital time, is essentially how much time the galaxy spend in a certain branch of the orbit. So essentially the 4 initial positions. We know, for example, that at the pericenter, the galaxy is much faster than when it is far away from the center. So that phase will have less weight than the initial position very far away from the center, because the galaxy is close to the pericenter for a shorter amount of time. A very high source of uncertainty is the last weight here. This essentially gives weight to the velocity of the clump. It tells us how many clumps are very slow compared to their galaxy and how many clumps are not. And this could be constrained from Muse observations or from other simulations like Ackermann et al. 2025, those kind of simulations that study the formation of the clumps. But even changing them, this is not a driving factor of the results in a sense. We can assume, for example, that all the velocities are equally probable, so we can have slow clumps, as many slow clumps as fast clumps, or we can give more weight to the clumps that are much slower than the parent galaxy, but these cause little variations. And finally, the simulations. That is, in the end, the simplest number because it's either a 0 or a 1, and the clump will become a wanderer or not. When we will perform a resolved simulation, this will be a number between 0 and 1 because we can also take into account the fraction of mass that was retained by the clump, so the tidal stripping in the end. Here we assume that the clump didn't change in mass, but the tidal stripping, of course, will reduce the initial mass of the clump. So if we put all of this together and some, let's say, the most likely values for these quantities, we get that since redshift 0.4, so within the last 3-4 gigayears, the jellyfish galaxies deposited about 10 to the 6, 10 to the 7 solar masses in wanderers. So this is a very little number, and indeed also in number of clumps, we talk about a few tens up to 100, some hundreds of clumps. So of course, as we will improve in the simulations, we want also to understand if the galaxies are if the clumps can be observed very well or not. So I think I ran out of time, so we'll just leave the sum. And essentially, we have observed the statistically relevant sample of clumps. We have shown that ramp pressure stripping can enhance star formation. We have seen the fireballs for the first time. We have seen that there is a lack of massive clumps, and we have also seen that very few clumps are likely to survive. Sorry, I think I went very beyond the limit of time, but thank you very much.
Thank you very much, Eric, for the very nice detailed talk. So now let's take some questions. Anna, please.
But then I come closer to the mic because we know how good it is. So
Yeah.
I have two questions. The first one is if these wandering clumps were to survive and become old clusters, maybe globular clusters or maybe ultra compact dwarf galaxies, how would we be able to differentiate them from normal globular clusters formed within the bolt or the halo of
Yeah.
a galaxy that was, I don't know, not disturbed?
Yeah, indeed, the project started to understand if this could be an exotic way to form globular clusters. In the end, we think that these objects are much less compact than globular clusters. The sizes are typically a factor of 10, even 100 larger. So their half mass radii are about 100 parsecs instead of a few parsecs. So this is the first signature that I would look at. They are much less compact than globular clusters. Other samples of dwarf galaxies, an important signature here is that they should completely lack of dark matter. So if we think about dwarf galaxies that are very ultra diffuse, I think the signatures of dark matter for them are not always present because of lack of data, difficulties in observations, but we should distinguish them because these clumps should completely lack of dark matter.
Thanks.
Hello, Eric. Really nice presentation. I'm starting my PhD and I'm working with jellyfish galaxies too, so really nice to learn a lot about it. I have, maybe it's a naive question, but can we expect that the slope of the mass function of these clumps depends on the J class of the jellyfish galaxy, depends on the stripping stage of the jellyfish?
Yeah, this is a very interesting question and would be very interesting to study. We see indeed that the driving mechanism seems to be the interaction with the intracluster medium. So I would say that, of course, a galaxy that is undergoing a strong ground pressure stripping should, in principle, maybe be more affected than one undergoing a milder ground pressure stripping. But all the 6 galaxies that you see here are of a large J class. They're all undergoing strong ground pressure stripping, so we weren't able to discriminate this kind of parameter, also because of statistics. Once you start selecting only clumps for which we have good estimate of the mass, only the tails, etc., it's also difficult to study the single galaxy. But that would be very interesting to study, sure.
Okay, thank you.
So I guess Nicholas has a question from Zoom. So can you unmute and say your question? Nicholas?
Oh, okay, guys. Can you hear me?
Yeah.
Okay, thank you. So thank you very much, Eric, for the very amazing seminar. So I wanted to ask you about that library of clumps that you built during your PhD, I imagine, right? To study the completeness and other factors of the clump mass function, right? So does this library rely on analytical models about what we know about clumps, or does it rely also on information that we have from observations? How does it work, like internally? I don't know. Do you expect that if the models that were used to create the library have some like weak points, let's say, tensions, I don't know, then this could affect the result that you got on those Gaussians later on?
Yeah, of course, in this case, the study of the completeness has been done by taking into account the results by Ariel, by Verle, in Verle et al. 2024. So if we wanted to build a model, we needed to know, given a mass and an age, what is the spectrum of these clumps. So of course we in this case we are biased by the fact that we used, for example, backpipes, even if Ariel did a lot of checks, varying the star formation history, varying some parameters. So we tried to test the models that we used in the best possible way. But we relied on the observations in the sense that we tried to mimic the clumps that we were seeing. So in terms of really the shape of the spectra. So we cannot say that we constrain the metallicity very well, but let's say I extracted all the spectra that I used for the study of the completeness from the real spectra that we obtain from the observations, with some interpolations to not be very coarse, let's say, in the extraction. But for sure, if one used a different models, I would expect variations in the results, even if not exaggerate variations. What I think it's possibly the main driver in the discrepancy that you saw between the observed mass and the intrinsic mass is most likely the definition of the borders of the clumps. Because these are clumps that have a very weird morphology, as you could see. So it was very difficult to define the edge of it. And especially for small ones, it's even more difficult because they are, the outskirts are immediately confused with the noise. So there could be some bias there, I would say, rather than in the SCD fitting model.
I see. Perfect. Thanks.
Any questions? No? Okay, then let's thank Eric for the wonderful talk.
Thank you. Thank you.
Thank you, Eric.
Very nice.
Thank you again, and hope we will see you again.
You again.
Bye. Thank you.
Bye-bye.
Yeah.
Oh.